Good day, everyone. In this video, I'm going to introduce to you an elementary concept on logic. Let's start first on elementary statement or atomic statement. Now, it is a sentence with a subject and a verb, and sometimes an object, but no connectives, just like and, or, not, if then, if, or if and only if. It's like, for example, Claire reads books. Another one, he answers her assignment. And then they understand the discussion. So these examples here are examples of elementary statements. Now for a proposition, it is a declarative sentence that is either true or false, but not both. When we say declarative sentence, it is a sentence that makes a statement or it expresses a complete thought or it provides a fact or it offers an explanation or it conveys information. Hence, when we say proposition, it is a statement or assertion that expresses a judgment or opinion whether it is true or false, but not both. So let's have here some examples. You have this statement here, Malay-balay is in Bukidnon. So this is a proposition. It expresses a complete thought. And we can tell whether this statement is true or false. So with this statement, we can say that it is true. Because Bukidnon is a province of Malay-balay. So Malay-balay is part of Bukidnon. Hence, Malay-balay is in Bukidnon. Next here, Malay-balay is in Davao. So this statement is false because Malay-balay is in Bukidnon. Malay-balay is not located in Davao. Another one here, 2 is less than 4. Actually, this is a mathematical statement. It expresses a complete thought, and we can tell whether this statement is true or false. So obviously, this statement is true. And the last one we have here, 4 equals 7. So another mathematical sentence or statement in which it is false because 4 is not equal to 7. Now, the truth or falsehood of a proposition is called its truth value. However, the following are not propositions. What is your name? So, actually, this is not a proposition. We cannot tell whether if this is true or false. Actually, this is a question. And next, do your homework. Still not a proposition. It is actually a command. And next, this sentence is false. Now here, we don't know what sentence you are referring. So when you say this sentence is false, we don't know that sentence, right? We don't know if that sentence is it really false or is it true? Hence, this is neither true nor false. Next is x is an even number. So for x, we know that x is a representation of any number. So it could be an odd number, it could be an even number, it could be a prime number. So we don't know what's the value of x. We don't know. It is just a representation of a number. So any value will do here. Hence, it depends on what x represents here. So we cannot tell whether this is true or false because we don't know what is the value of x here, because it is just a representation of any number. It is not just an even number. So in this case, this is not a proposition. And the last one here is angel. So it is very obvious, right? Because we can say that this is a name. It is not even a sentence here. So clearly, this is not a proposition. Now let's have here connectives. Connectives are used for making compound propositions. So the main ones are the following, where we represent here P and Q for the given propositions. Here you have proposition P. It means it is a declarative sentence. It is a sentence in which we can tell whether it is true or false. So there is a corresponding truth value for every proposition. So let's have here some connectives with their names, representations, and meanings. So first, let's have here negation. So for negation, we have this representation, and the meaning of this is not P. So for example, if P is true, the proposition, the statement is true, then its negation is false. And then next, we have here conjunction. So for a conjunction, this is the representation. This is the symbol for conjunction. And we can read this one as P and Q for conjunction. Next, for disjunction, this is the representation, as you can see, for its symbol here, it's opening upward, whereas a conjunction, it's opening downward. So for conjunction, this can be read as either P or Q, or you can also have both. So for the truth value of this, either P or Q is true, then this statement here, disjunction, is true. It could be either or at least one of them is true, then this becomes true. Or both of them are true, then this is true. Whereas here in conjunction, it is very strict. This will only be true if P and Q, the truth values of P and Q are true. So for conjunction. So for disjunction, it could be either or it could be both. Then here for exclusive or, this is its representation. Then the meaning of this is either P or Q, but not both. So in this case, for its truth value, this proposition is true if either P or Q is true. Now, if they have the same truth values, then this proposition becomes false. Next, we have implication or conditional. So this is the representation. This means if P, then Q. Or we can also read this as P implies Q. Now, P is the hypothesis. Actually, this is the hypothesis. This is our hypothesis in our sentence or state conclusion. So means P, our assumption or hypothesis, if P, then we conclude Q. So we have if P, then Q. And the next one here is what we call biconditional. For biconditional, as you can see here, there are two arrows to the left and to the right. So this means we have two conditions. Two conditions. First, we have P implies Q, or if P, then Q, and we have Q, if Q, then P. So this is what we mean by biconditional. We can read this as P if and only if Q. So take note for biconditional, there are two conditions involved here. Now let's try to illustrate negation or the connectives using the truth table. We mean truth table, it has truth values. So for proposition P, P here is a proposition. It is a statement, any statement. So of course, a statement could be either true or false. So there are only two possibilities for the statement. It could be true or false. So when the statement is true, its negation, we have not P for P, so its negation is false. When the statement is false, its negation is true. So as simple as that. Now let's proceed to conjunction. For conjunction, let's consider first the two propositions. We have P and Q. So we have here different truth value of the statements or sentence or the proposition. So here, when P is true and Q is true. And then another one here, when P is true, Q is false. Then here, P is false, Q is true. By the way, when we say F, it means false. When we say T, it means the truth value of that proposition is true. So here, false, false. Now let's try to determine the truth value of the proposition for P and Q. Conjunction, this is P and Q. Again, as what I have said a while ago, when we say and, so for this connective conjunction, the truth value, so this means P and Q. So this proposition is only true when both, but this is both P and Q. And so when P and Q are true, the truth value of P and Q, then this proposition is true. So again, when the truth values of P and Q are true, both are and, then this proposition P and Q is true. Then the rest, false. So as you can see here, both P, proposition P and Q, the truth values are both true. Therefore, our compound proposition P and Q is true. Then the rest, false. So because there exists at least one false for P and Q, if there is one false in the proposition, then the resulting compound proposition becomes false, as you can see here. Now let's proceed to disjunction. So disjunction, we have or. So to determine, by the way, this we have here given two propositions P and Q with their corresponding truth values. So to determine the compound proposition P or Q, let's used the definition a while ago, or the meaning of this. So for P or Q, either P or Q, it means either P or Q is true, then this proposition P or Q is true. Also, if both propositions, the truth value of both propositions are true, so this proposition becomes true. Now look at this table here. Both, we have here in our meaning both. If both is true, then the conjunction, this junction rather, is true. The truth value is true. And then here, either P or Q is true. So we have here P is true, then this becomes true. P or Q becomes true. Here, there is true here, therefore it is true. Now here, all are false, all truth values of the propositions are false, then it is false. Follow? So for this junction, or at least one proposition has truth value true, T here, so we can write true. And then if there is no true in the proposition, if the proposition, the given propositions are all false, then we have false. So please do not be confused in conjunction, because in the conjunction, it's very strict. It is only true because and, we're working on and. It is only true when both propositions have the same truth value that is true. So if the truth value of the proposition is true, or both true, so it only it becomes true here in our compound proposition, and the rest false. But here in this junction, or, so if there is only one proposition that is true, therefore our compound proposition is true. And then it is false when all the propositions are false. So let's proceed with the next connective. We name as exclusive or. So exclusive or. So let's try to consider here the truth value of the given two propositions. So we have this. So T, we have TF, FT, and FF. So to determine the truth value of the compound proposition, we have this exclusive or. Let's recall the meaning of this for exclusive or. We have here either P or Q, but not both. So it means either P or Q is true, then this is true, but not both. It means if they are both the same, or they have the same truth value, it means this becomes false. It should be not both. So as you can see here in our table, take note here that they have both the same. Both propositions here have the same truth value. Hence, the truth value of our compound proposition exclusive or is false. It should be either P or Q. So either true, here it is true. So we have here true, so it is true. Then here both are false, it is false. So here, please do not be confused here to our disjunction. Take note for our disjunction here. Disjunction here, it is either P or Q or both. So take note, this is non-exclusive or. So yung the previous one is exclusive or, but for disjunction, this is non-exclusive or. Why? Because it's non-exclusive, because we consider if both propositions are true. It is true, right? The previous one for exclusive or, take note ha, both propositions are true, just like this one. Our compound statement is true. But in our exclusive or, it is not both. It means when both propositions are true, it is false because not both, exclusive or. And also, this is false. So this is the only difference for disjunction for non-exclusive or. Next, let's have here implication. So for implication, consider again the two propositions with its corresponding truth values. Then for the compound statement, if P, then Q, we have this in the last column. So here, if our hypothesis is true, then the conclusion is true. This makes our compound statement P implies Q, or if P then Q, true. And then if the hypothesis is true, if true, then Q is false, it will make our compound statement false. So here, if P is false, then Q is true. Hence, our compound proposition is true. Another one, if P is false, then Q is false. Our compound proposition is true. Now, take note here in our implication, there is only one false truth value. That is when the hypothesis is true and then our conclusion is false. So because you are assuming that your statement is true and then you are concluding here the statement is false. So that will make our compound proposition false. Okay? So whereas here, you're assuming or your hypothesis is false, but then you are concluding that Q is true, the next proposition, then our compound proposition implication is true. So again, we only have here one false as our truth value in this table. Only if when P is true, then Q is false. Now let's proceed to biconditional. For biconditional, consider again the two propositions P and Q. Then the last column here is what we call the compound proposition for biconditional. Take note, we have here two arrows here, if and only if. So we have here when P is true, if and only if Q is true, then the resulting compound proposition is true. Another one here, true if and only if Q false, resulting is false. Here, P is false if and only if Q is true, the resulting is false. And P is false if and only if Q is false, then the resulting proposition for biconditional is true. Now, as you observed here, the resulting or the compound proposition for biconditional is true when both propositions have the same truth value. So you can see here, the same truth value, it is true. The same truth value, even if they're false, they're the same, the truth value of the compound proposition is true. However, here, they're not the same, they are false. Now, try to compare the table for exclusive or and for biconditional. So let's try to compare them. So each proposition is true. Here, true, true. Whereas for biconditional, the proposition is only true when both propositions have the same truth value. So they are most likely, or they are opposite, right? For exclusive, the compound proposition is only true when either P or Q is true. Here, it is false when either P or Q is true. However, it is true when both of them have the same, both of the propositions have the same truth value. Okay, so this is the summary of the compound propositions with connectives. So this is for not P when we have here given truth values of the proposition. We have P and Q for conjunction. This is P or Q for disjunction. So this is the notation for exclusive or. Then this is for implication or conditional. And then the last column is for biconditional. So the next is tautology. So what is a tautology? So a proposition is said to be a tautology if its truth value is T. It means true for any assignment of truth values to its components. For example, let us try to show whether this compound proposition here is a tautology. It means in the last column, all the truth values are true. So you can see all are T in our truth table. So let's consider here a proposition P. So since we want to show that this is a tautology, the proposition involved here is only P, proposition P. So since there is only two possibilities for a proposition, it could be true or false. So we have this. So for not P, again, negation, when P is true, not P is false. And when P is false, not P is true. So for or, this is disjunction. Let's have here the last column. So we can say that this compound proposition P or not P is a tautology when all the entries here are T, are true. So we will recall rather our discussion a while ago. We have here TF. So for TF, P or Q. Q here stands for not P. Okay, so we have TF, TF, so T. Next, we have FT. FT here is T. Or if you will not use this table here as your guide, you can just go and memorize or notice that or, when we say or, if there is only one proposition, if there is only one truth value of a proposition that is true, so say for example, P here, P is true, then our compound proposition, this one is true. Or, for or, either one is true. So this is true. So as you can see here, in our last column, as you can see, all are T. The entries are all T. It means the truth value is true or T for any assignment of truth values to its components. So as you can see here, we have here any assignment of truth values. So TF, we have here FT, truth values to its components. So any assignment, the resulting here for our compound statement, we have T in the last column. So if you have here another components here, another components, another row here, and then all entries in the last column are T, it means this compound proposition here, the one that is above, or located above this column, is a tautology. So if you have many components here with their corresponding assignment of truth values, and then you have a resulting here T, 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 so it is a tautology. But if there exists just one F here in the last column, we cannot conclude that this proposition is a tautology. Okay, so let's have here the next term. We call it as contradiction. So a proposition is said to be a contradiction if its truth value is F or false for any assignment of truth values to its components. So this is the opposite for tautology. For tautology, we mean in the last column, all the entries are T. So here in contradiction, we are looking for all the entries that is false. So all the entries in the last column should be F or false, so that we can say that the compound proposition is a contradiction. So to illustrate it, let's consider an example. So we will show that P and not P is a contradiction. So again, let's have here a proposition P because only P is involved here. So we have TF. And then for not P, for the negation, we have this one. Then for the last column, to determine the truth value of the last column, we can use the table, or you just use the meaning of this connective. So we have here TF. Again, and, because this is and, conjunction. For and, it is very strict, right? Because you can only write T here or true if both of them are true. Both of the propositions are true. So since they have different truth value, so this is F. Or if we use the table, we have TF here. Take note, Q here is not P in this proposition. So TF, as you can see here, F. And then we have FT, so not both, it is false. So FT is false. Next, contingency. Now, a proposition that is neither a tautology nor a contradiction is called a contingency. Now, take note here for our contradiction, the last entries in this column are all X or false. Hence, we can say that it is a contradiction. And if you have here another components here with the assignment of truth values, and then it should be the last column should all be false or F. So you can conclude that this compound proposition here is a contradiction. Now, if there exists just one entry here that is not false or it is T, then you cannot conclude that it is a contradiction. Rather, it is a contingency. So it is neither a tautology nor a contradiction. So, for example, show that the proposition P, if P rather implies not P, is a contingency. So consider the proposition P with its corresponding truth values, true or false. And then for not P, we have this one. So for the compound proposition, if P, then not Q, we have here, so let's try to recall our table. So TF, again, Q here is the same as not P. So, or our not P here is Q here in this table. So TF, so this is false. And then FT, right, this one is true. Or again, as just what I have said a while ago, if we have no table for our basis, the only false statement there in our compound proposition is when P is true, the hypothesis is true, and the conclusion is false. So it becomes false for our compound proposition conditional. So here, as you can see, the last column here entries are F and T. Hence, this is not a tautology nor a contingency, rather a contradiction. Again, this is not a tautology because the entries are not all T. Also, it is not a contradiction because the entries here in the last column are not all F. Hence, this is a contingency, a combination of F and T for the last column of your truth table. So let's proceed. Let's have here logically equivalent. So when is the propositions logically equivalent? So here, when two compound propositions have the same truth values, no matter what truth value their constituent propositions have, they are called logically equivalent. So for the notation, we have this one. So let's have here an example. Show that the propositions here, not P or Q, and not P, and not Q are logically equivalent. So we have this notation here. So we are going to show this one. So let's start first here in the left side. So not P or Q. So let's construct a truth table. So again, we do have two propositions here, P and Q. So we will make P and Q and its corresponding truth values. So we have here T, T, F, F, then T, F, T, F. Actually, we constructed this one for all combination of truth values. So we have TT, TF, FT, FF. So since we want to show this one, we want to find the truth values of this compound proposition. So we will do first the innermost. So we will find this one, P or Q. Since we have here the truth values of P and Q, so we will construct another column for P or Q. So here for P or Q, so again for or, it means either P or Q, right? Either P or Q. It means if there is just one T, or it could be at least one T in the proposition P or Q, then the truth value of this compound proposition is true. Follow? So just like this one, T means T here in the compound proposition. So we have here, there is one T. So we have T here, one T. We have T here. And then here, there is no T for any proposition P and Q. So we have here F. Now the last one is to find not P or Q. So here, not P or Q. So we will construct again another truth table for this. So column, the last column here is the negation of this column. So because we have, we're done P or Q in this column, so we will negate this column. So again, for the negation of true, it is false. It is false. Negation of T, F, and then the negation of false is true. Hence, we have here the truth value of our compound proposition, not P or Q. Now, next, we will construct a truth table for this compound proposition on the right side. So here we go. Again, we will consider two propositions here, P and Q, because it's in the given. So P and Q, we have all these combinations of truth values. Then, okay, here, why we constructed here the not P column? Because we are to find not P and not Q. So first, we will construct the truth table of not P. Next is for not Q before we can get this compound proposition N. So here, for not P, we're going to focus on the first column for truth values of P, proposition P. So we have here the truth value of T is F. Here T becomes F. Here F becomes T, F, T. Now let's proceed to the next column. We will create not Q, truth value. So here, we have here, for not Q, we will be focusing on this column here, in the second column. So again, not Q, T, the not Q of here, T is F. F becomes T here, T becomes F here, then F becomes T here. So we're done for not P and not Q. So we will be constructing the last column for this compound proposition. So we have this one. So since we're done finding the truth values of not P and not Q, we will connect them. Connect natin na siya by using this connective and. So for and, as what I have said a while ago, when we say and, it's very strict in terms of its truth value. It should be that not P and not Q are both true, so that this compound proposition becomes true. So here, as you can see here, they are both F, so obviously it's F. Here, they are not both F, they are different. As what I have said, for and proposition or connective rather, you can only have true when both propositions have true truth value. So obviously this is F and the next one is F. And here they are both true for and connective, so it becomes true. So we have here the truth values of this compound proposition. And then we are going to compare the last columns of the two truth tables here. So we have this one and this one. Now, When two compound propositions have the same truth values, no matter what truth value their constituent propositions have, then they are logically equivalent. Now, in this case here, as you can see, they have the same truth values. So we have here F, F, T, T. So in this case, we can say that these two propositions here are logically equivalent. And we can write our final answer or conclusion as this one. So let's have here the next. Now for the converse of a conditional proposition, we have here if P then Q. So the converse of this is the proposition if Q then P. Now notice here, P is our hypothesis, right? And Q is our conclusion. So in that case, we have here, again, I will write here, this is the hypothesis, and Q is our conclusion. Now, if we are going to get the converse of this, the hypothesis here becomes the conclusion here in the converse. And the conclusion here becomes the hypothesis of our converse. So for the contrapositive of a conditional proposition P implies Q, or if P then Q, it is a proposition not P, if not Q rather, implies, or again, if not Q, then not P. So that is the contrapositive of the conditional proposition here. So please do not forget this one. So for example, let's consider a proposition P, which is Kate is from Malaybalay. And then our proposition Q is Kate is from Bukidnon. So, by the way, Bukidnon is a province of Malaybalay. So Malaybalay there is part of Bukidnon. So Malaybalay is one of the cities of Bukidnon. So for the proposition, conditional proposition, P implies Q, or if P then Q, we can have this statement. So we have here, if, so this is our P proposition, then we have here our Q. So if P, then Q. So we have here the statement. Now we are to find the converse of this statement. Now for the converse of this statement, we know that the converse of this conditional proposition is this. We have if Q, then P. So we will switch. The hypothesis becomes the conclusion, and the conclusion becomes the hypothesis. So here, it becomes, if Kate is from Malaybalay, then Kate is from Bukidnon. So here, Kate is from Bukidnon is of course our Q proposition, and then Kate is from Malaybalay is our P proposition. It means Q implies P. So for the contrapositive of this, we know that this is the contrapositive of our conditional proposition P implies Q. So we have here, if not Q, then not P. So the statement there, by the way, before we can get the statement of our contrapositive, we will try to find the not Q proposition and the not P proposition based on the given P and Q proposition. So here, for P proposition, the negation is Kate is not from Malaybalay. Then for Q, the negation is not Q. It means Kate is not from Bukidnon. Hence, we can construct our contrapositive statement. So we have here, if Kate is not from Bukidnon, then Kate is not from Malaybalay. So here, Kate here is not from Bukidnon is our not Q. Then Kate, again, we have here, if not Q, then not P. Now, let's try to look at the truth value of its proposition. the truth value of the converse, and the contrapositive. But before that, let's determine first the truth value of our given conditional proposition. If P, then Q. So for this, the truth value is, because as what I have said a while ago, Bukidnon is a province of Malaybalay, and Malaybalay is just one of the cities of Bukidnon. So here, Malaybalay is in Bukidnon. Now, if Kate is from Malaybalay, then of course it is true that Kate is from Bukidnon. Therefore, this statement here is true. This proposition is true. Now, let us try to determine the truth value of our converse. So for the converse, we have here, if Kate is from Bukidnon, then Kate is from Malaybalay. Now, take note, Bukidnon is a province. So if Kate is from Bukidnon, then is it always true that Kate is from Malaybalay? Just try to look at the statement there. Here, for Q implies P in the converse. So if Kate is from Bukidnon, it doesn't follow that Kate is from Malaybalay. Why? Because if Kate is from Bukidnon, Kate could be from Valencia, where Valencia is still in Bukidnon. It could be she is from Maramag. Maramag is still part of Bukidnon. Or she is from Quezon, Bukidnon, still part of Bukidnon. So it doesn't imply that if Kate is from Bukidnon, she is always from Malaybalay. So it does not imply all the time. Hence, this statement is not true in general. So since this is not true in general, we can say that the statement is false. Okay? Now let's have here for contrapositive. If Kate is not from Bukidnon, so she is not from Bukidnon, of course, she could be outside from Malaybalay. She is outside rather from Malaybalay. She is not from Malaybalay. Because she is not from Bukidnon, it is always true that Kate is not from Malaybalay, right? So this statement here is always true. So for converse. So in this case, given the conditional proposition if P, then Q here, if this always follow that our contrapositive proposition is always true. It's not true in general for the converse of the conditional proposition if P, then Q. So that's it. Next is predicate or propositional function. So it is a statement containing variables. For example, we have here a mathematical statement, x plus 2 equals 9. So actually, this is a statement because it expresses a complete thought. So it contains a variable x. Another one, x is greater than y. So another predicate that contains two variables, x and y. So we represent a predicate by a letter followed by the variables enclosed between parentheses. It's like we have here p of x. Another, we have p of x, y, and the like. So in our example, we can represent the first predicate here by p of x here. So this statement here is p of x. And the other one, we can represent this one by q of x, y, because we're using here two variables, x and y. So whatever variable or variables we are using, we need to reflect it in our notation for predicate. Next, let's have here existential quantifier. So for the representation, we have this one. So this is the representation of the existential quantifier. And this reads as there exists x such that p of x. Another one, we can also read this as there is some x such that p of x. And we could also have for some x, p of x. For example, let's have here the predicate containing variable x. So we have here x minus 5 equals 2. Now take note here that x is representation of any number. So we could have x equals, say, 5 or 6. We could have x equals, say, for example, 6. Then this predicate becomes 6 minus 5 equals 2. And we know that 6 minus 5 is 1, so this is false. Another one, we can also let x be equal to 7 or any real number. So we have 7 minus 5 equals 2, and we know that 7 minus 5 equals 2. And this statement here is true. Now take note that for any representation of real number here for x, the statement or the predicate x minus 5 equals 2 could be true for some values of x or for some value of x. So there exists a value for x such that 7, so a value for x which is equal to 7, such that this predicate here or proposition is true. So x minus 5 equals 2. Okay, again, there exists only a value of x which is 7, such that this predicate here becomes true. And that value is 7. Hence, we can write here, there exists x such that x minus 5 is equal to 2. So we can write this statement. And we use existential quantifier. Okay, take note we can only use the existential quantifier in this symbol here. It means there exists, there is some, or for some. We can only use this one if there exists a value of x in which the predicate becomes true. Hence, it is not true in general. No, it is not true for any value of x, for any real number x. So from the word itself, existential, the existence of that value to which our predicate becomes true. Okay, now let's proceed to the next. Next is what we call the universal quantifier. So for the universal quantifier, we have here our representation for, this is inverted A. So we can read this one as for all x, p of x. Another one, for every x, p of x. For each x, p of x. For any x, p of x. So from the word itself, universal, it means it is true to all, for all. So for example, we have here a predicate u of x. We have here the square of x plus 1 is equal to x squared plus 2x plus 1. Now, in this case, if we are going to substitute any real number for x, any value for x, this equation here or this predicate here is always true. So say for example, if we substitute it when x is 1, so we have 1 plus 1, the square of 1 plus 1 is equal to 1 squared plus 2 times 1 plus 1. So this is 2 squared. Then we have here 1 plus 2 plus 1 is, of course, 4 is equal to 4. So it is true. True when x is 1. Then you can try another value for x here, any value. And then you will notice that this equation is always true, is always equal for any value of x. Hence, for this predicate here, we can write for all x. So it depends, ha. If it is x, we're using variable x, you write here x. But if you're using y, you write here y. So for all x, the square of x plus 1 is equal to x squared plus 2x plus 1. It means for any value or for every, here for every, for each, for any value of x, for any real number, if we are going to substitute it to the equation, still the equality holds, or the predicate is always true for any value of x. So for all. That's why we're using here for our quantifier for all, for the universal quantifier. So it satisfies our equation, or it or the predicate is always true for any value of x. So please do not be confused here, because for our existential, there exists an element, or for some values, our predicate is true. So it is true only for some. But here in our universal quantifier, it is true for all, for any values of x. So that's it. So we're done. Thank you for watching. God bless everyone.